Okay, everyone. So we're gonna, last time we talked about AX equal to B, and we specifically talked about trying to ill condition the AX equal to B. And what we did is some MATLAB coding just to show what would happen when you try to break this backslash solver, right, that we have built over a long period of time. And one of the things that you saw there was that, in fact, we've worked very hard to build well-conditioned, stable algorithms for solving AX equal to B because it's such a fundamental part of everything we do in terms of solving computational problems. It all comes down usually to an AX equal to B solve. Now, what's interesting about that AX equal to B solve is when you solve a square matrix n by n, so we're going to go now to the n by n case, one of the things that you see is that what the backslash does, which is a very nice command, it actually takes that matrix A and does an LU decomposition first. And so what I want to talk about is how do you accomplish the LU decomposition? So up to this point, we've talked about how to do an SVD decomposition. We've talked about a QR decomposition. And then for these square matrices, LU factorization is one of the things that you really want to know how that's done and how it works in practice. So that's what we're going to talk about today, is basically solving AX equal to B. And in particular, we're going to really talk about this connection between Gaussian elimination and LU factorization. And what I'm going to show you is that Gaussian elimination in its process is able to generate for you an LU decomposition. And so we're going to talk about that algorithm. And it's interesting, it's going to look a lot like what we did for householder triangularization in the structure of how we do this. So the idea of LU decomposition is take this matrix A and write it as a product of two matrices, L and U. So L is lower triangular, and U is upper triangular. I'm going to actually impose one more restriction on L, which is the diagonals are 1. Okay? So it's got this lower triangular and upper triangular form. Now, why is this important? So when I'm going to solve AX equal to B now, if I have this decomposition, what you're going to see is basically going to amount to solving this with the LU decomposition is solving AX equal to B is equivalent to doing a forward and a backward substitution in two different problems. Okay? So here's how it works. You take this A, you say, I'm going to take this A and I'm going to solve AX equal to B. Well, A itself is LU. X is equal to B. I'm going to define UX to be a new vector Y. So I'm going to have UX is equal to Y, and then I'm going to have LY is equal to B. So what I've done in doing this factorization and declaring this to be Y is now I have two linear systems of equations. But here's what's special about these two linear systems. This is in lower triangular form. This is upper triangular form. So if I wanted to solve these, then all I have to do here to get the solutions is do forward substitution. And for once I get that solution, U itself is upper triangular, and I can get X then by backward substitution. So that's the nice thing about this is what I have in this decomposition is something that in fact allows me just to do substitutions to get the answer. What's the cost of substitution? Well, the cost of substitutions, we'll look at this when we get to the triangularization, but this basically scales like order n squared, each one of these. So there's two operations of order n squared, whereas when you do Gaussian elimination, it's typically an order n cubed operation. So if n is large, This is typically significantly faster. So that's why we like it. I'll make a side comment here that if we go to MATLAB to solve these, what's nice about this is if I want to get the solutions to this, what I can do is to get y, I just say y is equal to L backslash b. And then once I have y, I can put it in here to get x is equal to u backslash y. Remember, the comment I made last time in class is the backslash is really kind of sophisticated. So when you do this, it looks to see, can I just solve this by forward or backward substitution? And it sees like, oh, look, I can. So let me just do this operation here. And it's smart enough to know that all it has to do, instead of trying to do an LU or a Gaussian elimination, it already sees that all it has to do is forward substitution. Where when it gets to here, it says, oh, all I have to do is backward substitution. These are order n squared operations. It does it, and then you have your solution. So that's a nice thing to take advantage of. When you have MATLAB, it already is looking for this structure. And so there it is. It sees it and exploits it in getting a solution. Okay, so this is the idea of LU, is if I can get this, then I have a faster way to solve AX equal to B. And the way to get this LU decomposition, as I'm going to show you in a minute, it looks a lot like Gaussian elimination. In fact, as you go through the process of Gaussian elimination, normally what we do is we don't keep track of constructing this LU, but Gaussian elimination, when you do it, your goal is to produce an upper triangular matrix, something that looks like U. And then you do backward substitution. That's what Gaussian elimination taught us how to do. Now what we're going to do is keep track of the operations L that allowed us to produce that upper triangular form. And that's what we want to talk about now, is an algorithm that does this. Okay, so I'm going to erase this, and we'll start going through this process. Okay, so what we're going to first start with is we're going to say we're going to be working with an A matrix. And let's go ahead and say that this A matrix is an M by M. Okay, so it's a square matrix, M by M. And what we want to do is start thinking about how would I go and produce this decomposition. So first of all, let's talk about what we would normally do in Gaussian elimination and what we would also do in LU. And that is in particular, what I really want to do is take somehow this matrix A, and in Gaussian elimination, your goal is to turn it into some upper triangular matrix through a set of operations. So one way to represent that is the following way. You say, I want to do a series of operations which I will represent by these matrix multiplications. So I multiply by L1, then by L2, L3, all the way to L of m minus 1. And what these operations are trying to do is take this matrix A, turn it into an upper triangular form. So this is exactly what we do in Gaussian elimination. The question is, we've probably not thought about it this way. What we did in Gaussian elimination, right, was we find the dominant pivot, make everybody 0 below it. Go to the next pivot, make everybody 0 below. So you go down, go down the diagonals, and you just make everybody 0 below the diagonals recursively. Okay? In some sense, though, this is the mathematics of how to do that and the operations you use to do that. What I want to think about is that this matrix here, I'm going to call L inverse. So the product of all these matrices, I'll call L inverse. And if I can compute these and compute this, then I can invert this to give me A equals LU. So I would love to figure out a way that when I invert this, I can produce a lower diagonal matrix. And that's exactly what we're going to show how to do in this process, is construct a principal set of matrix multiplications. How do I construct each one of these such that I recursively make this thing upper triangular form and such that when I invert it, it's a lower triangular matrix. So it feels like I'm asking a lot of this process, but you'll see we can do all of this by appropriate construction of these matrices L1, L2, all the way to L of n minus 1. By the way, if this is the inverse L minus 1, if I take the inverse of that, then L itself here will be something like this. L1 minus 1, L2 minus 1, all the way to L m minus 1. So that's what L is going to be when I take the inverse of this. Okay? All right, so we're on our way to producing this LU decomposition. So let me just draw this out graphically, much like I did when we did householder triangularization. I'm going to draw matrix A. And I'm going to show you what multiplication by L1 does, then by L2, then by L3. And we'll do a 4 by 4. So let's start off with some matrix here. I'll just illustrate it on a 4 by 4. It's a square matrix. This is A. What I want to do is hit this matrix A with matrix multiplied by L1. So when I multiply this by L1, here's what I want L1 to do. I want L1 to make zeros of everybody below the first column, first element of the first column. So I want to leave this alone. All these should be 0. And then we have some values here. So this is L1 acting on A. When I had it with L2, I want to go now to the next diagonal, next pivot point, which is this second diagonal, make everybody below that 0. This is exactly what we were doing when we did Gram-Schmidt's orthogonalization. If you go back to that lecture, you can see it has a very similar feel and structure to what we're trying to do. Make zeros appear by some appropriate matrix multiplication. So if I multiply by L2, then I get zeros down here, and this is L2A. And then finally, hit it with L3. So this is L3 acting on A, which is now in upper triangular form. So this is the process also of what we did exactly in Gaussian elimination. Remember Gaussian elimination, the idea was you pick the pivot, make everybody below it 0. Then you go to the next pivot, which is the next diagonal term, which is here, make everybody below it 0. Then you pick the next pivot here, make everybody below it 0. So that's what we did in Gaussian elimination. It's just that now we want to track those operations with these matrices L1, L2, L3. Okay? Because at the end, what we get here is this upper triangular form, and this is our U matrix in the LU decomposition. So we have the U that comes out. We just have to figure out how do I get the L1, the L2, and the L3. And boy, doesn't it look a lot like Gaussian elimination. Take this, make things 0. Take this, make things 0. And in fact, you'll see very much the structure of Gaussian elimination shows up here. All right. So I need to know how to construct these matrices. And that's what we need to work on next, is how do you actually put those matrices together? Okay. So here we go. I want to construct LK. Now I'm going to constrain the look of LK. In fact, what I want LK to look like is I want LK to look something like this. One's on the diagonal. And in the kth column, what I want here is minus L, K plus 1, K, all the way to minus L of M, K. I want some numbers here. So everywhere is 0 except for the kth column. Underneath the 1 here, there are these numbers. And what are these numbers? Well, what these numbers are going to be, I'm going to show you here. L, J, K is equal to x of jk or x of kk. So when I go to the kth column, this is the ratio of the diagonal term divided by the term I'm looking at. Now, the reason this is important because this is exactly what you computed when you did Gaussian elimination. If I want to take two columns and I want to make one 0, I have to make the two numbers in that column the same. That's the multiplication you do to make two numbers in a column exactly the same. Okay, that's exactly what we did in Gaussian elimination. And then what we do is add and subtract the rows, whichever we do. Like we could multiply the column by the negative of it, add the rows, or multiply by the positive and then subtract the rows. And then that's how we got rid of the zeros below the main diagonal, is by using that ratio of this is the diagonal term, this is the term you're trying to eliminate. Okay? So, another way to think about this. I give you the matrix A, whose columns are x1, all the way xk, all the way to x of m. Okay? So I have these columns, and what I want to do is say, what do I want this operator right here, this linear matrix multiply, to do to that matrix A? Notice it's identity everywhere except for one column in particular, the x of k. So nothing gets expected here except for the x of kth column. And that x of kth column, here's what's going to happen. So I have x of k, x1k, x2k, all the way to xmk. And when I hit this with L of k, here's what I want to get back out of this thing. I want L of k, x of k, which is equal to x1k, x2k, and then all the way down to x of kk, which is diagonal, is 0 everywhere else. So you see what I did here? If I pick this right and hit this with L of k, it zeroes out all the terms below the diagonal term, which is xkk. And that's what these are intended to do. Notice, if I put these in here, what's going to happen is it's going to basically say, when I come to the xkk term, the xk of minus 1, if I want to eliminate it, I figure out what do I have to multiply that equation by to make it look like xkk, and I subtract the equations, and that's what you get. This is a Gaussian elimination procedure right there to eliminate everything below the diagonal. So you're using the value of the diagonal, and you're figuring out for each column, how do I add or subtract these columns to get these rows together to make everything 0 below there? And this is the matrix that does it for you, right there. So it's a very, in my view, super clever construction of this matrix to do this. And by the way, here, let me just put some, K is between J and M. Okay, so it's all the terms below the diagonal. So there you go. People thought about this for a long time, and what they just did is just said, okay, instead of when we do Gaussian elimination and we go down the diagonal, pick the pivot, make everything 0, and we can just add or subtract columns as we wish. Now, here's a formulaic way to do Gaussian elimination But now what I'm doing, instead of just doing the Gaussian elimination column by column, I'm keeping track of this matrix LK that did that elimination process. So every time I do a step of the Gaussian elimination to eliminate zeros, I get a new L of K. So I get L of 1, removes all the zeros in the first column below the diagonal. L of 2 removes all the values below the diagonal in the second column, and on down the line. And now what this allows me to do is keep track of it, because there, in fact, is the matrix that does exactly what we've been doing in Gaussian elimination since we took our first course in linear algebra. Okay. All right, so that's the procedure. That's what the matrix looks like. And so let's keep going on this, and let's start defining some more terms here, or figuring out how to do this from an algorithmic structure. By the way, one quick comment. That matrix L of K, remember when we did householder triangularization, we constructed also a matrix. Remember, we constructed these matrices P1, P2, so forth, to do our householder triangularization and get our QR decomposition. In that case, each matrix multiplication was by some projector, and that projector, right, was a unitary operation. This is not. That's one big difference between what we did then and what we're doing now. This is just eliminating everything below the diagonal, and that L that I wrote down there is not a unitary operator. It's not an orthogonal projector. So that's really important to know, okay? All right, so let's keep going on here then. So I want to write that process down in a more compact form. So I'm going to define a vector, L of K. It's going to be zeros everywhere until you get to K plus 1, K, L of M, K. So in other words, the diagonal term will be LKK. So all the terms below the diagonal, here they are. Okay, so zeros everywhere below the diagonal, where would be the diagonal term. So L of K is going to have our matrix multiply is going to be defined as follows. This is capital L of K. It's going to be the identity. Remember, I had ones all on the diagonal. So it's going to have the ones on the diagonal minus this here, which is L of K times E star K. And this here is the unit vector in kth direction. So what this is an outer product. L of K is this way. You're laying E of K as a row vector. When you take this, this is a matrix, so you get identity minus this matrix, which is exactly what I drew for you. I already erased it, but that was the L of K. So it's zero everywhere. This says go to the kth column. It's the only place that's going to add something, and add this to it, which is these numbers below the diagonal. So you have ones on the diagonal because of this. Add this vector to the kth column. So these pop in below the diagonal. Okay, so that's a more compact representation of what we want to look at. By the way, notice also how this looks very similar to an orthogonal projector. It's not, but it has the kind of structure that we were looking at before, right? Which is you take a vector X and you project it into a space orthogonal to the vector you're looking at, but now you're doing something a little different. Taking I minus this direction, which gives you that vector. And so what we're going to do is that's going to allow us to zero out everything below the diagonal in a principled way. Okay? So that's what the L of K looks like. And that's what we want to use for computing this LU decomposition, because the LU is going to be a bunch of these together. Okay. One thing I want to note here is that's the outer product we do. But if you were to do an inner product, in other words, E of k star L of k, that's 0. Because here, everything's below the diagonal, so there's no overlap. E of k is 1 on the kth column. This is 0 on the kth column. It's non-zero on the k plus first and onwards. So when you take this inner product, this is just 0. So the inner product is 0. The outer product is is this thing here on the kth row, kth column. Okay, so now here's this little stroke of luck. That's what Trefethen calls it too, but it's kind of awesome. So I'm going to say this because notice when we get these L of k's, if you remember, there was this issue, which is when I'm going to compute L is L1 inverse, L2 inverse, all the way to L of k minus 1, sorry, L of m minus 1 inverse. So this is supposed to be my lower triangular matrix, but I have the L of k's, but look, after I get them, I've got to compute the inverses. So the question is, so I get this matrix that I'm going to construct by here, but I actually, when I'm going to try to write down what L is supposed to be, I actually have to produce its inverse and then multiply all these together, right? And what I'm looking for is, my hope is that this thing is lower triangular. So I'm going to show you an observation or a little fact of the data, which is super clever and nice of the way this was constructed. And you'll see that actually computing the inverses themselves are lower triangular. And then the multiplication of this together is trivial at that point. So here's the observation you want to make. So we have this observation. Outer product is this. You have this inner product. Okay. So here's what we're going to do. We're going to consider multiplying I minus L of k E star of k. So this is the outer product. So this is I. This is the L of k that we had. Okay, I'm just writing it here, but I'm going to multiply it by another vector, another matrix that's made in a very similar fashion, which is I plus L of k E star of k. So the only difference between these is the sign flip. So instead of having minus of this guy, I add plus of this guy. Okay. So this L of k, remember, that looks like this. 1's on the diagonal. And then this L of, which row am I in here? K plus 1, k to L of m, k. This one has a minus sign. This one has a plus sign. So the only difference between these is these are plus or minuses. It's the same matrix, just with a sign flip. Okay? So I'm going to take the one that has the minus sign and multiply it by this one here, which has a plus sign. So I'm just taking this matrix, multiplying it by itself. One has a negative sign, one has a plus sign. The reason I'm going to do this is become absolutely, hopefully clear in a moment. When I multiply these together, what you end up doing, do the multiplication out, you get your I squared, which is just identity again. Minus, you get the cross terms cancel actually. You have plus this and minus this. And then you get this, minus L of k, E star of k, L of k, E star of k. And this here is 0. When you do this multiplication out of these four vectors, outer products, inner products, this just becomes 0 because you have this inner product. So when you multiply these together, the main observation is this then just results in the identity. So if I take a matrix and multiply it by another matrix and I get the identity, it means that this other matrix is the inverse of this matrix. Okay? So in other words, the inverse of this matrix is I plus L of K E star of K. So in other words, these inner products, or sorry, these inverses are actually trivial. All you got to do is flip the sign. So there was a negative sign here, make it a plus sign. That's it. That's very nice because this is still lower triangular. That's lower triangular, that's lower triangular. The inverse is very easy to compute and partly was constructed that way, so this would be easy to compute. Okay, so again, that's the matrix we're working with. It's ones on the zeros everywhere and just one column here. This has some really nice properties that I'm showing you. And this is what makes this LU decomposition. This is the algorithmic way we do Gaussian elimination. So when you solve AX equal to B and you are doing Gaussian elimination, essentially you are working with that matrix. Okay? All right, so we have this matrix. Now let's come back to here and decide how to compute this. So I'm going to erase these things and then we'll keep going. Okay. So I've figured out how to write the L of K. And if you remember, this is what L now is. Okay, so we said we are going to do this LU decomposition. This L was this, where U was after you've done the Gaussian elimination and put an upper triangular form. That's U. And the question is, what were the collective set of operations that made that happen? These were the operations. But if you compute all this, which is the inverse, L of K, the inverse is this is with the plus sign, and the straight application was the minus sign. So now if I take the inverse, which is going to be a plus sign, and then I multiply these together over and over again, what you end up with is this matrix L is simply going to look like the following. Ones on the diagonal, L2, 1, L3, 1, LM1. Then you have the diagonal 1, and then you have L3, 2, all the way to L, sorry, 2, yeah, sorry, this should have been, yeah, no, okay. So now, yeah, 3, 2, all the way to M2, and so forth. Okay, and then 0 up here. So this here is the L matrix. One's on the diagonal, and it's because you've constructed it that way. And then these guys that are off the diagonal show up here at each single column below that diagonal. Okay, so this is your matrix L. This is the matrix that is doing Gaussian elimination for you. It's the matrix that when you multiply it, L1 times L2 times L3, it's recursively going through and zeroing out all the elements below the diagonal, one at a time. Zero out everything below the first diagonal, second diagonal, third diagonal, all the way through. And of course, at the last column, you don't need to do it. That's why it ends at M-1, because once you're at the last column, you just leave it. So there you go. That is LU decomposition. A couple facts. Let's talk about how long does it take to do this? Well, when you do this, think about what you do, the process of Gaussian elimination. What you do with Gaussian elimination, you start off with this main diagonal, and you pick it, you make everything 0 below it. So you're going to say, if I make everything below it, I have to go row by row and add 2 equations, as it were, in the next row. So I'm going to go across this way and down this way. So if there's n by n, I'm going to have n operations here, n operations there. So it's order n squared. But then I'm going to go down the whole diagonal, which is n of them. So this operation count is roughly order n cubed. You can make this a little bit more accurate, right? You can find that, in fact, it's order some alpha n cubed, right? You can actually work hard at finding what that number is. The main thing, though, is it scales like the cube. So if your matrix doubles in size, this is 8 times more expensive. Okay, that's something you have to keep in mind when you do these computations, because that adds a lot of computational time just by making your matrices bigger. Okay, so that's the Gaussian elimination procedure, or the LU factorization procedure. It's expensive. But once you've done it once, you can keep solving, and oftentimes this is the context you're doing this in, is you're often solving this problem where you keep changing the right-hand side. So you do one time, once, and then after you've done the factorization to get the LU, now you can solve this over and over again in order n squared time, because you're just doing forward and backward substitution. Okay, so again, if your matrix, if n is like 1,000, then this will cost you, this is 1,000 times more expensive to just keep using backslash versus getting the LU decomposition and then using the LU over and over and over again. This is what you want to be doing here, is get the LU, reuse it, because it is expensive to get, and it's a lot cheaper to solve this AX equal to B once you get it. There's LU. Pretty nice, right? And again, all we're seeing here is all these tricks, like QR factorization is just Gram-Schmidt. LU is really just Gaussian elimination. They have fancier names because there's kind of there's a broader abstract structure to this, and an uber concept to be gained if you can do these factorizations, because you can take advantage of them in a more principled manner for doing your computations. All right, we're going to stop there. Take questions.